Okay, hi everybody, welcome back. We're in chapter 4 or 4.5, we call it. It's really the last part of the chapter 4 vectors chapter, and we're dealing with relative motion, which was in the last video notes segment. And this is going to be about something that should be familiar to you, but we're going to apply it now to vectors, and that is position and displacement vectors. So what we mean by position vectors is a vector that simply serves to tell you where an object is. For example, right here. This vector describes where an object is. So we call it a position vector. It's some distance x and it's some distance y. So we'll call that, I don't know, our initial x hat and our initial y hat right here. Some distance x, some distance y from the origin. Okay, and the same is true of this R final right here, this final position. It's merely telling you that it's some distance in the x direction and some distance in the y direction from the origin. So we'll call that R final x hat and R final y hat right here. Those should really have arrows over them too. Okay, so you can tell a position vector because it refers back to the origin. All right, it tells you where something is with respect to the origin, as both of these do right here, and that's what this equation tells us right here. It's just some distance x and some distance y. Which brings us to the idea of a displacement vector. If you have an initial position and a final position, then it should make sense that a vector can describe the path that goes from initial to final, and that we should be able to call that the position, the displacement vector. Now we're calling these R. In past chapters, we've called displacement delta x or delta y. We're just calling this R from here on out because we're dealing with enough x's and y's as it is. So R initial, R final, R or delta R, they mean either position or change in position. And so it should make sense, like I said, that like we know from previous chapters, our displacement vector, delta R, I should do that in a different color. That should be described as the final position vector, all right, minus the initial position vector right here. And if you look at that, we have this initial position, and then we have plus a change in position. All right, so let's write this down here. R initial plus delta R equals RR final, right? Doesn't this vector from the origin plus this vector equal that? It sure does. We've been doing that for seemingly weeks now. It hasn't really been that long. Okay, but if you want just your change in position, oops, get rid of that. If you want just your change in position right here, then that should make sense that it's R final vector minus R initial vector. And that's exactly what we have here right down at the bottom. And you know how to add and subtract vectors because we've been doing that in unit vector notation. You subtract the x hats, you subtract the y hats, and you have an answer. All right, so change in position is our R final minus R initial. In the same way, we can have a velocity as well, because we know that velocity is a change in position over time, right? Now this formatting got a little bit messed up right here. This should say, since delta R is a vector, then that means that our vector average velocity must also be a vector because, or as, delta R is something times the scalar. All right, it's multiplied times the scalar of 1 over time. All right, so what does that mean? So we have our displacement vector here. We have this time 1 over change in time. What's going on here? Oh, okay, well that's just delta R over our change in time. We recognize that as being equal to our velocity right here. Okay, so time is just a scalar. There's no direction change, so that means whatever direction that your displacement is going in, then that's the same direction that your velocity is going in. Look here down at the bottom right here. All right, here we have an object taking kind of this weird path like that, and all position 1 is saying, that should really be labeled R1. All that's saying is the object is going that direction there, and down here it's going kind of this direction. Who cares about what caused it to change its position? All we care about is the initial position and the final position right here. All right, so if you draw a straight line between initial and final, you'll have your change in position, or you might call it your displacement. But you could also say that if you take that displacement and divide it by time, like we did up here, then you could draw another vector that is it's basically parallel to that, and call that your average velocity. Because if you're going to be displaced down the road north, all right, then you must have a velocity in the north direction. That only makes sense. So in the next problem, this video unit, or this video segment is going to go up to example 4.54, which is the next one. We'll see how those two vectors are actually related. All right, so we've got a dragonfly right here, and it has an initial position right there, and it's got a final position right here. All right, now notice that they're stated using unit vector notation. Something something x hat and something something y hat, and the same with this final one right here. Okay, so the question is, what is the displacement? Okay, what is the delta r vector, and what is the average velocity? What is that? Average velocity right there, we want to find out. Now, in previous problems, we may have taken this, the problem may have said something like, all right, take these and turn them into magnitude and direction notation. All right, so you could use your Pythagorean, and you could use your inverse tangent to do that, because you have x and y components. But we're not going to do that. We're going to use them just as is, because our change in position is described as our final position minus our initial position, right? You remember that from chapter 1 or chapter 2. So why can't we just take these unit vectors right here and just subtract them out? All right, so that means we are going to be subtracting our initial from our final. So we're going to subtract something x hat, and we're going to subtract something y hat right here. What is that something? All right, well, it's our final x hat, so that's negative 3.00 meters. Subtract the r initial x hat, right? That's 2 meters, 2.00 meters. That's a poorly drawn minus sign in between there, but so that's subtracting. And then we're going to do the same thing for our y hat. So our y hat is 5.50 meters minus 3.50 meters, and that's a subtraction we have for the y hat direction right there. So let's just simplify this and see what we get. All right, so that means our displacement vector delta r should be, so negative 3 minus 2, that's negative 5.00 meters in the x hat direction. And we've got, what's it, 5.5 minus 3.5, that's 2.00 meters in the y hat direction right here. Okay, so it's moving negative x and positive y, so something like that. All right, we don't really care. All we care about is the fact that we have the x and y values, and so we can do a lot with that. So this is really our answer right here for change in displacement. That vector can be described as a negative 5 and then a negative 5x and a positive 2, so it's going that way. So you could think of it like that, but we're going to keep this in unit vector notation for a reason, because remember, the average velocity is very closely related to change in displacement, right? I mean, average velocity is simply change in displacement delta r divided by our time, right? So why can't we take our x and our y components, that is x hat and y hat, and simply divide them by the amount of time that's been elapsed? All right, let's go back and look at our problem right here. How much time does this change in displacement take? It takes 3 seconds. All right, 3 seconds later, it's at a different position. So let's write out our delta r in unit vector notation in the numerator. So that is negative 5 meters x hat all right, and 2 meters y hat, 2.00 meters y hat. And now let's take that and let's divide that by the amount of time that's elapsed. 3 seconds and S3, no, 3S, 3 seconds and 3 seconds right there. This fraction, x hat, and this fraction, y hat, now describes the average velocity. All it's left to do is really just to simplify it right here. Okay, so the average velocity vector can be described as thus. What is negative 5 divided by 3? Well, I get negative 1.67. Negative 1.67 what? Well, it's something x hat, right? But what are the units? Well, remember, it's velocity, and so it should make sense that we have meters per second right there, all right? Meters per second. So that's going to be our units, which makes sense because this is a velocity. Let's do the same thing for the y hat, and then we'll be done. So what's 2 divided by 3? That's 0.67. All right, 0.67 what? Meters per second, and that's in the y hat direction right here. So we've written a unit vector, or we've written a vector in unit vector notation for average velocity because we very closely related it to the unit vector for change in displacement because they are closely related. So that's it. That's example 454. Look for the next one, which next problem, which I believe deals with a rainbow trout. That should be 455. And the next video segment and the next video notes will be on more displacement and acceleration vectors in unit vector form as well. So thanks for watching. Let me know if you have any questions, and I'll see you next time.